So, up until now, I've told us why we need to understand the measurement process in quantum field theory better. I've told you why it's difficult to do that without providing a concrete QFT compatible model of detection. And I've talked about the two state-of-the-art detection models, right, which will help us solve this issue. So now let's see how that all works here in terms of measurement chains, which I think is the right way to think about this. So earlier I claimed that for non-relativistic quantum theory, these pragmatic modeling concerns I'm talking about have all been sorted out in terms of measurement chains and the Heisenberg cut. Unfortunately, I don't have time to really argue that they've provided an effective solution there, but I'd like to see how that solution maps onto the relativistic context here. To review, a measurement chain is a sequence of steps in our experiment which sort of carry measured information from one regime into another. Right? So to give you an example is that we have an atom in a superposition that we're interested in, and it emits a photon which is detected by a photomultiplier, which triggers a small current, which turns on a transistor, which, and so on and so on. And this ends up displaying a number on a screen, right? I think most experiments can be thought of in these sort of sequential terms, and we just need to understand the interactions between different elements in this sequence, right? So, at some point along this chain, we typically take a Heisenberg cut, where we switch from modeling things in a quantum way to a classical way. And now, look at this diagram here. This is the sequence of events which happen in our experiment. Atom interacts with light interacts with photomultiplier interacts with small current interacts with transistor, and so on, one thing interacting with the next until we get to the computer screen. So the x-axis here is along the sequence of our measurement. It's roughly along the sequence of time, right? It's not about complexity. It's not about size of the system. It's not about number of degrees of freedom. It's just a sort of temporal sequence of our experiment, right? So at some point in modeling our experiment, we switch from modeling things in a quantum way to modeling them in a classical way, right? And this would be a probabilistic classical way when we make this Heisenberg cut. Because remember, I'm not trying to explain here why we get definite outcomes for experiments. I put that in the realist part of the problem. So when we come to this classical model, we're coming to a probabilistic classical model of what's going on here. So there's nothing fundamental about where we place the Heisenberg cut, as long as we place it late enough after the last quantum phenomena, then we should get good predictions out of this, right? And the later we put it, the better. So again, I'm just worried about pragmatic issues here. I'm not saying the world switches from being quantum to being classical. I'm saying at some point in our modeling of the measurement, we treat it as such. Right? So what I'm suggesting here is that when we model measurements which involve quantum fields, we need to make a relativistic cut. When we cross the QFT to non-relativistic quantum mechanical divide, at some point we're going to need to make a relativistic cut in complete analogy with the Heisenberg cut. So here I'm considering we have the Higgs boson, which interacts with something, and at some point along the measurement chain, we switch to modeling things in a non-relativistic quantum way, and we go on a bit, and then later we'll switch to modeling things in a classical way and end up talking about computer screens and different probabilities of different outcomes there. Right? So again, I'm saying there's nothing fundamental about where we place this cut, as long as we place it late enough after to the right of the last QFT phenomena, we're going to get good predictions in general. Now, one thing that should be noted here is I said earlier there's no description of light in non-relativistic quantum mechanics, right? So if at some point you have a bunch of atoms emitting photons and we describe all of that in QFT, those photons then all travel together in the same direction, and there's enough of them then that we can describe it classically as a classical electromagnetic wave, right? Then in this, because there's no non-relativistic quantum model of light, we actually have to jump from our quantum field theory description of all this collection of photons over into a classical model. We jump directly from the bottom line to the top line. So the relativistic cut and the Heisenberg cut, they can be taken at the same time, where we jump from this relativistic treatment of the light in quantum theory to a treatment of light in special relativity up here, and we jump both of them at once. because again, there's no light on this non-relativistic quantum line. So again, there's nothing fundamental about where we place this cut. As long as we take it late enough, it's good. And it doesn't have to be before the Heisenberg cut. It can be at the same time. Possibly it could be after. I just want to make this analogy here. So using this, how can we see the Fuster-Virch and the underdewitt models in this understanding? The Fuster-Virch models an interaction between two quantum fields. And so what it does in this understanding is it moves us along the bottom rung. We have quantum field theory number 1, which then interacts with quantum field theory number 2, and the measurement process moves along through that process. On the other hand, the underdewitt model couples a non-relativistic probe system to a quantum field, and so in this diagram it makes a diagonal jump upwards, right? There's an interaction between one system here on the left and an interaction between the system on the right. One of them is in QFT land, one of them is in non-relativistic land. You have these two theories, we have 1 foot in each theory, and we're trying to make them couple to each other and talk to each other, right? So this switch from quantum field theory to non-relativistic quantum mechanics, it happens during the interaction between these two systems. So that's a diagonal jump. And I want to contrast that with what's missing from those two is this third way of moving upwards on the diagram, is to cross the divide vertically. So the underdewitt detector crosses during an interaction. This one crosses between interactions, is what I'm saying. So I'm saying we take an isolated quantum system here. So we had some quantum systems before which interacted, and we described all of that in QFT. And then we get to this quantum field theory number 4. And then we're going to make some sort of non-relativistic approximation or non-quantum approximation to jump us out of this quantum field theory description, but it's just considering this QFT number 4 in isolation, not in interaction with anything else. We make some non-relativistic or non-quantum approximation of this thing to jump up the line, and then with this now approximated version of our experiment, we continue on modeling in a non-relativistic way past that. So we take this jump vertically, not during an interaction. While this is possible for some low energy, free, massive QFTs, we can't yet do the same thing for interacting bound states, like the hydrogen atom. As I mentioned, we don't have a very good second quantized description of the hydrogen atom. So we have a good first quantized approximation, which we could put up here, but down at the bottom here, we don't have a second quantized thing. So we wouldn't even know how to describe what goes on down here. We don't even know what to put down here at the bottom, which means we are precluded from finding a map between this thing we don't understand and the first quantized hydrogen atom that we do understand. Right? So, can we do enough with these tools? As I see it, these are really the only 3 tools that we have available currently to model the measurement processes involving quantum fields. Right? We have the Fuster-Virch probe, which keeps the Fuster-Virch framework, which can keep us down here on the bottom rung. We can sometimes make these diagonal jumps with underdewitt detectors whenever that's appropriate, and we can make these non-relativistic approximations sometimes, although these are not as well understood as they should be. So each of these 3 tools have their limitations, but as I see it, these are the only tools we have available. So are these tools enough to bring home the experimental spoils of all of the successes of quantum theory and to restore evidential support and physicality to quantum theory? I'm just going to leave that as an open question. All right. So, okay. So, and this is a great question. If you can think about this and find out the answer, I'd love to hear it. I think this is a very interesting question we need to answer. I think it's a critical question. So, in conclusion, I've argued that in order to bring home the spoils of experimental success for quantum theory, we need to better understand how to model measurements which involve quantum fields. This unavoidably means we need to talk about how to model detection in QFT. Otherwise, at worst, we're making moves which are banned by QFT and have no real possibility of being supported. Or at best, if we don't make those mathematical blunders, we don't really have an explanation of anything. We haven't explained how our model or our detection system works. We've just identified some analogous or matching object in quantum field theory that we hope it will line up with. There are two state-of-the-art detector models being used today, the underdewitt detector and the diverge detector. Together with some non-relativistic approximations, these may or may not be enough to guide us across the sort of relativistic cut that I think is necessary to really understand how we should be modeling our experiments involving quantum fields. Okay. Any comments or questions, I would take them in the YouTube comments if you have them. And here are the references for the talk, the full references if you want to go look those up. Okay, thank you.